is 8 tunes problem. So I have already started the recording. So the video will also be shared anyway. It's going to be a simple topic, and it is also a kind of interesting problem. So before going into the 8 tunes problem, I have to just introduce you to the various techniques of algorithm designing. So right now you are learning data structures. So we haven't looked at these topics. But when you go to another semester where you will be studying the algorithms, analysis of algorithms, in that subject, you will come to know about these various techniques. So these are different ways by which you can devise a solution for various problems. For example, divide and conquer is used in quicksort. So when you have to sort a large list of numbers, you can divide them into small lists and sort them individually, and finally you can merge them to make it into a single list. So similarly, there is one such technique called backtracking. So backtracking is actually already listed here, and the reason that I'm highlighting backtracking is that we are going to solve the 8-tune problem by applying backtracking concept. Idea of backtracking is very simple. Like you do not know uh, the direction you have. For example, assume that you are in a maze. Okay, you are in a maze and you have to get out of it, and you don't know which path is correct. So what you will generally do is that you will choose some random path. So you'll choose path one, and we'll see whether it take you to the destination. If not, you will come back to the original status, and then you will start choosing the exploring the other option. So backtracking is just this, that you try to randomly try various options, and whenever you find that a certain option is not appropriate for the expected solution, you immediately revert it. Okay, that is, you reverse the decision and you go back to the original state and then start taking a new decision. This is the idea of backtracking. Now, what is the problem of 8 tunes? So the 8 tunes problem is such that you are given a chessboard of 8 by 8. So 8 rows and 8 columns are there in that particular board. Your task is to place 8 tunes on the board such that no tune is in attacking position to another tune. So each of the 8 tunes are in a safe position, and no tune can be attacked by another tune, which simply means that you can place only one tune in each row, because you know the various movements possible for a tune. So you can place one tune in each row, and the next tune has to be placed based on the previous tune. So this is the basic idea, and actually this is the solution you will have to produce. The solution is like this. So you can see clearly that you have placed the 8 tunes in each row and row, but they are not in any they are not attacking position against other tunes. So this is the expected solution, a result for the problem. But it's easier to devise or find the solution manually by applying your brain, but we have to find an algorithm to get the solution. That is the challenge. So we have to develop some kind of an algorithm through which we can get this solution. And we are going to employ backtracking for developing that particular solution. So there are different ways this can be solved, but today we are going to take one particular approach to solve the problem. And also we are going to simplify the discussion by reducing the problem to 4 by 4 chessboard, because it will be very tedious to discuss the 8 by 8 solution. So we are right now going to discuss 4 by 4 implementation, but it can be very much extended to 8 by 8, because the idea is going to be same. So we are going to just discuss about this particular simplified version, and we are going to use both the stack and the backtracking logic. And you can also imagine that a stack is a natural data structure for backtracking, because you know that in stack the removal always happens from the top. So pop operation means that you remove the most recent element from the stack. So backtracking is always implemented with the help of stack. Okay, now we are going to commence the solution for the 4 by 4 problem. So step 1, we are going to place the first queue in row 1. But we don't need to consider anything for the case of first queue because it is the only queue currently available. So it can be simply placed in the first row, first column, and that position is also pushed into the stack. So step 1 is completed. Queue 1 is placed in first row, first column, and that information or that position is recorded into the stack. Now step 2 is obviously we have to find the location for the second queue in the second row. We can't place it here. We can't place it here because it's going to be attacked by the queue. So we can place it in the third column in the second row. That is what happened. This explanation you can go through when you get the PPT. So basically that is what they have done. That they have identified that third column in second row is what is the appropriate position for the second queue, so that it will not be in the attacking range of the first queue. So and that is also pushed into the stack. Now we need to find a location for the third queue, but unfortunately there is no position for the third queue in the third row because either it can be attacked by first queue or it may be attacked by second queue. So what we do is that we now apply the backtracking concept. So we backtrack the previous queue, that is second queue, and we change the position to like this. So we change the position of the second queue to fourth column in the second row, and that is also updated in the stack operation. So previous input was a previous element position was removed from the stack, and the new position gets inserted into the stack. So we now have to look for a position for the third queue, and that is now available. So previously we could not find the position, but now it can be found. So the third queue can be safely positioned in the second column of the third row, and that is also pushed into the stack. And now fourth queue, but once again we have reached the dead end situation. So there is no position to place the fourth queue in the fourth column in the given arrangement. So we have to apply backtracking. So we have to backtrack when we try to place queue in row 4, we find that all positions are guarded. We therefore backtrack to the queue in row 3 and try to find another place for her. Because queue in row 2 is guarding both column 3 and 4, there is no position for queue in row 3. So it is not possible to backtrack the third queue. Now we have to do the backtracking of the second queue, but we have already done it. So we eventually go to the first queue and change her to second position in the, that is second column in the first row. That is what happened here. So ultimately the only option we had is to go all the way or backtrack all the way to the first row and change the position of the Q1 itself to second column. And now we have to continue the process. So we need to find the position for the second queue and third queue and fourth queue. So the second queue is positioned like this. Third queue is also positioned, and we finally got the solution. I think that picture is missing. So in this order, we can place all the 4 queues in different positions such that they won't be in attacking position against each other. So this is the manual solution we have found, and we have applied the concept of backtracking with the help of a stack. So I think you can now imagine how this can be extended for a 8-queue problem. Just a matter of more number of queues, but approach is same. So the basic idea we have followed here is that generalizing the solution, we see that we place a queue in a position in a row and then examine all positions in the next row to see if a queen can be placed there. If we can't place a queen in the next row, we backtrack to the last positioned queen and try to position her in a next column. And then we repeat it. So if there is no room in the next column, we fall back again. So this is the strategy we followed for this particular problem. Now finally, we can express the logic in the algorithm. So the algorithm, since it is in a pseudocode, it's much easier to write it. Only writing a program will be little more difficult. Uh, you have to convert everything into the logic, proper logic. So this is just a pseudocode based algorithm. So this algorithm will run till the row less than or equal to both sides. That is, until you place all the queues in all the rows, this loop will execute. And in each iteration of the first inner loop, the outer loop, the inner loop will run for this condition. Loop column less than or equal to board size and the row less than or equal to board size. So what we are actually, why this second loop is actually used is that in each iteration of the first loop, we will try to place the tune of that particular iteration in a particular column of the current row. And if that happens, then this condition will not be violated. That is, the column value will remain less than or equal to board size. But if that cannot be achieved, then this condition will become true. That is, column greater than or equal to board size. That is, we have the column value has exceeded the maximum range. That is 4, if it is the case of 4 before, or 8 in the case of 8 by 8. So, and we could not place it. So, okay, first, what if you are able to find a valid position, then place the queue at the row column intersection on board and push that value into the stack. So push stack, row column into stack and increment row. So as long as we are able to find the locations properly, this loop will keep on going. But the moment you reach the condition that the next queue cannot be placed anywhere, then this loop will be triggered. So loop column greater than or equal to board size. That is, you have exceeded the board size and you could not place the tune. And now what we have to do? Backtracking. So that backtracking is what done here. Pop stack the most recent position of the tune from the stack and remove the tune from the board and go back to the loop again. So you will try to find a new position for that particular tune. So this is what we actually implemented in the sample problem. So with this, we are completing the topic of 8 tune problem. I hope you don't have any doubts on this. If you have any doubts, you can ask them now. So with this, the topic is covered. I'll share the PPT as well as the video shortly. Just giving few minutes for you to ask any doubts in this particular topic. After that, I will wind up the session. And also, if you have any doubts regarding the test plan pattern, you can also ask them.